Yeah, thank you. So thank you all for coming again, hear me. So now I'm talking a little bit more technical today. So I'm going to talk about linear decision rules, which is a package I've been developing with Joaquim. So first things first, it's maybe a particular case of what we have already seen this morning on infinite models. But let's talk about stochastic programming. So a simple model for stochastic programming is stochastic linear programming. And here it's an even more simplified problem. So you minimize the expectation of something subject to equality constraints and positivity. So this is just your standard linear program stochastic. You have a decision X subject to random constraints and possibly random costs. So if you're thinking about infinite models, you could have like infinite parameters for C, A, B, and X is going to be an infinite decision as well. So the whole framework of linear decision rules is that you try to write the uncertain parameters as functions of some underlying vector xi, and you like the decision to also depend on this uncertainty after observing it. So it's kind of a recurse action. So you replace this like standard formulation that I gave you with this like functions of xi form, and where everything now depends on xi, and you have this big xi here, which is the support of your uncertainty. And now, for simplicity, we're going to assume that the constraint matrix is deterministic, just to make our lives easier, but actually our modeling life easier as well. And we also suppose that the parameters are going to be linear functions of this. This is not such a huge hypothesis, just kind of a reparameterization of what your uncertainties are. And if you do that, you also like linear systems so much that you use a linear decision rule for your variables x. So x of xi is going to be a matrix capital X times xi that you have to find out. So with all of that, you replace this in your optimization problem. You see here that you have an equality constraint. You can kind of cancel the xi's out, but you cannot actually cancel these xi's out in the same way. So you have to do a little bit more. So, but the trade-off is that you're like replacing a fully flexible decision that could be any function by this very simple model, but it will lead to a more tractable optimization because now you can use duality and some trace tricks to replace the previous like infinite dimensional model, which has this xi and the expectation, with this one, which has the expectation of your random variable. And this is something that you can calculate offline. And then you will optimize with this thing being reduced to a known matrix. So this problem is much easier to solve. And the purpose of our linear decision rules package is to allow for like a straightforward formulation of a stochastic optimization problem that will then allow us to like get this X matrix out naturally. So it's a jump extension. We have introduced this LDR model, which is kind of an extension of the jump model. And we also extend the variable macro to allow for declarations of uncertainties. I'll just show you in a moment how this is like in syntax. But then we put two new attributes because we might also want to have this dual linear decision rules, which have kind of dual roles for the primal. And we have this extra function get decision to extract the coefficients. So the whole purpose of this linear decision rules is to be like a small package that exposes a lot of its internals that is very easy to manipulate if you need to build upon it some of your favorite application. So this is another energy example in this conference. I'm sorry for that, not being too imaginative today. So we have this like standard jump modeling problem. You have these initial and final volumes. You have thermal and hydro generation. And the like new things is that you have this, you import linear decision rules. You create your model with this LDR model. You declare the inflow uncertainty with an extra parameter in the variable, and you assign a distribution from it. And you write your constraints using this inflow variable wherever you need it. So this looks like very natural formulation, and that's kind of our point here. And to solve it, we set the attributes for solving. So for instance, here it will solve only the primal version, but you could solve both of them. When you call optimize, you set your favorite optimizer. The resulting problem is going to be a linear programming problem. So almost anything will work. One of the cool things is that we also allow for like quadratic forms in the objective. So I didn't show you here, but you could also have quadratic terms. Actually, the example has quadratic terms, so it's not exactly the same formulation. And that's why we are using IPOpt here and not just a general linear programming solver. And then you can get the decision. So you can have both the constant term and the linear coefficients. And we kind of show here some checks just to illustrate how you get the decision of your linear programming problem. So this is a linear decision rule for your stochastic optimization. And so how does the package itself work? That our point here was having something that's kind of easy to understand so that you can like hack upon everything. So if you're like the modeler, you write this LDR model, which is a subclass, subtype of abstract model. And the thing that it does is that it reads your model and it builds some extra caching information for you to be able to extract all the components that you're going to need when you build this linear decision rule. So it's using jump extension. And then we extract from here the matrix data of your problem. So A, B, C, and Q. Q is the quadratic form for the quadratic problem that you have. And it looks a lot like LP matrix data, right? It's probably very much copied paste from there. And then we added this quadratic part. Then the package will take this matrix data and formulate the primal and dual linear decision rule models. So there's a part of here which is not completely explicit is how you transform your distribution into this matrix M. But if you're using a standard like Julia distribution, you can have queries for the expected values and the variances that will allow you to build this like psi transpose matrix. So you formulate this, and then the package will pass the resulting models to your favorite solver, and you'll optimize on top of that. And then if you're like the user, you can query the resulting linear decision rule back in the variables that you created, because the model that is going to be formulated here will have like different variables, and you'll have a map that maps the variables that you declared in the LDR model to the variables that are going to correspond to the solution of your like true optimization problem that you solved down here. So there's this small interface back so that you can complete the loop and get your solution in terms of what your actual variables were. So the next steps we're thinking about is first handling correlated uncertainty. So for the moment, we only have like independent one-dimensional things, and that's a very easy starting point. And the general setting is like a product of independent vector uncertainties, but there are still some kind of outstanding issues on what's the best way to integrate that into a formulation that will allow for like a general transformation between the model that the person is writing and the calculation of the expected M matrix. And then further steps in the orthogonal direction, a little bit orthogonal, is having multi-stage decision rules. So the first like low-hanging fruit is having two-stage optimization. So you start with a here and now decision x0, which doesn't depend on uncertainty. That's probably very easy to hack on, but it's not yet done. And in general, if you are multi-stage, you have decisions xt that depend only on the past. So the observed uncertainties xi1 to xt. So this is kind of a nice generalization, and that's something that we'll hope to implement. And there's kind of a dependency here. If we have like correlated uncertainties a long time, then it's nice to be able to construct them in the first place. But then that's a different thing. So with that, that's the link for our GitHub repository, and I'll be happy to take your questions.